Hi viewers, Masal Khan welcome you on Mizan TV with a new video lecture on transmission switching and signaling. In this lecture we will discuss about the transmission media. Before starting the lecture, it is requested to please subscribe the channel and press the bell icon so that all the videos reach to you first. A transmission media is defined as anything that can carry information from a source to a destination. As we discussed in the physical layer of OSI model, that physical layer is responsible for the transmission of electrical signals through transmission medium. So this diagram shows you the physical layer connection with transmission media. The transmission media may be cable or air. This diagram classified the transmission media either guided or unguided. The guided media consists of twisted pair cable, the coaxial cable, fiber optics cable, while the unguided media is a free space. The subject of wireless communication best covers this transmission medium. Now in this slide we are discussing the guided media. So guided media, which are those that provides a conduit from one device to another, including twisted pair cable, coaxial cable and fiber optic cable. Physical connection is required in guided media. A signal traveling along any of these media is directed and contained by the physical limits of the medium. This point is more important as the physical limits of the medium restrict the transmission rate. The transmission rate in twisted pair cable is slow while in optical fiber is high. Twisted pair and coaxial cable uses metallic or copper conductor that accept and transport signal in the form of electric current. Optical fiber is a cable that accepts and transports signals in the form of light. All these mediums are analog medium using the concept of wavelength division multiplexing. Now, a twisted pair consists of two conductors, normally copper wires, each with its own plastic isolation, and then twisted together. As shown in the figure, one of the wire is used to carry signal to the receiver, while the other is used only for a ground reference. The receiver uses the difference between the two. In twisted pair cable, interference due to noise and crosstalk may affect both wires and create unwanted signal. If the two wires are parallel, the effect of these unwanted signal is not the same in both wires, because a wire, either transmission line or ground reference line, which is near to the interfere area, is more affected while the other is less affected, and the difference of both wires will be more high. Twisted pair brings the concept of twisting the both wires. By twisting the pairs, a balance is maintained between both wires. Now, in one twist, one wire is closer to the noise source while the other is farther. But in the next twist, the other wire will be closer to the noise while the first one will be farther from the noise. So the balance is maintained between both wires. There are two types of twisted pair cable, which are UTP and STP. UTP is known as unshielded twisted pair cable, which is the most common twisted pair cable used in communication. UTP is upgraded by IBM as shielded twisted pair, or simply STP. As figure shown, STP cable has a braided mesh covering that encases each pair of insulated conductor. A metal casing improves the quality of cable by preventing the penetration of noise or crosstalk. The STP cable is more bulkier and more expensive. This slide shows the application of twisted pair cable. A twisted pair cable are used in telephone lines to provide voice and data channels. A telephone local loop commonly consists of unshielded twisted pair cables. The DSL line that are used by the telephone companies to provide high data rate connections uses the high bandwidth capability of unshielded twisted pair cables. Now we are moving to coaxial cable. Coaxial cable are announced as coax. The construction of coaxial cable is totally different from those of twisted pair cable and those of TP and STP. Due to this different construction, coaxial cable carries signals of higher frequency ranges than twisted pair cables. Coaxial cable has a central core conductor of solid or standard wire, as shown in figure. This is a copper wire which is enclosed by an insulating sheet. This copper conductor is encased in an outer conductor of metal file or braid, or a combination of both. Outer metal wrapping serve both as a shield against noise and as the conductor which completes the circuit. This outer conductor is also enclosed in an an insulating sheath, and the whole cable is protected by a plastic core. A fiber optic cable is made of glass or plastic and transmits signals in the form of light. Optical fiber uses the concept of total angle reflection. In optical fiber, as figure showed, a glass or plastic core is surrounded by a cladding of less dense glass. The difference in density of the two materials must be such that a beam of light moving through the core is reflected off the cladding instead of being refracted into it. The figure shows the communication between a sender and receiver by using the optical fiber cable. The center consists of a core inside which is surrounded by cladding. The signal is starting from sender to receiver by using the concept of reflection. Now, what is the total angle reflection? When a ray is moving from more dense area to the less dense area, it is reflected. There are three basic principles of reflection in physics. In the first case, if the angle of incident is less than the critical angle, the ray refracts and moves closer to the surface, as shown in figure 1. If the angle of incidence is equal to the critical angle, the light bends along the interface. If the angle is greater than the critical angle, the ray reflects, make a turn into the more. The term step index refers to the suddenness of this change in dense area and travels again in the substance. In optical fiber, there are two propagation modes. The one is single mode and the other is multi-mode. The multi-mode is further divided into step index and graded index. The figure C shows the single mode of propagation. The single mode carries light pulse along a single path. In multi-mode step index fiber, the density of the core remains constant from the center to the edges. A beam of light moves through this constant density in a straight line until it reaches the interface of the core and the cladding. At the interface, there is an abrupt changes due to a lower density. This alters the angle of the beam's motion, which contributes to the distortion of the signal as it passes through the fiber. The figure A shows the step index in detail. In the multi-mode of optical fiber transmission, the density of the core is not same in the multi-mode graded index for optical fiber. It is decreases towards the edges of the core. The word index here refers to the index of refraction. As we saw in the figure, the index of refraction is related to density. Therefore, there is varying densities as there are varying indexes. Density is highest at the center of the core and decreases gradually to the lowest at the edge. Figure shows the impact of this variable density on the propagation of light beams. Optical fiber is more widely used in data communication. These are often found in the backbone networks because of its wide bandwidth and cost effectiveness. With optical fiber, we can transfer data at a rate of 1600 gigabits per second. The advantages of optical fiber are higher bandwidth, less signal attenuation, immunity to electromagnetic interferences, resistance to crossover materials, lightweight, greater immunity to tapping. The disadvantages include the installation and maintenance, the unidirectional mode of light propagation, and the cost. Now we are moving to the unguided media. As we know, the unguided media transport electromagnetic waves without using a physical conductor. This type of communication is often referred to as wireless communication. Different forms of electromagnetic waves that are used to transmit data are radio, satellite, microwave, Bluetooth, and infrared light. The figure shows the electromagnetic spectrum. The radio and microwaves are starting from 3 kHz to 300 GHz. The infrared is starting from 300 GHz to 400 THz. From above infrared, there are light waves up to 900 THz. Now we are moving to the propagation method required for wireless communication. The first propagation method is the ground propagation. In ground propagation, radio waves travel through the lowest portion of the atmosphere, almost hugging the earth. If we see the diagram of ground propagation, the low frequency almost below to 2 MHz signals follow the curvature of the planet. The distance covered by the signal is directly depend on the amount of the transmitted power. In the sky propagation, the signal is reflected from ionosphere. Higher frequencies among 2 to 30 MHz radiate upward into the ionosphere where they are reflected back to the earth. Sky propagation allows for greater distance with lower power. The most important propagation method for cellular communication is line of sight propagation. In line of sight propagation, very high frequency signals are transmitted in straight line directly from antenna to antenna. In this type of propagation method, a direct physical contact of the effective curvature of both antennas is required. This slide shows the electromagnetic spectrum for radio waves and microwaves, which is divided into 8 bands, each band regulated by government authorities. Each band is regulated by government authorities ranging from very low frequencies to extremely high frequencies. Very low frequencies and low frequencies from 3 kHz to 300 kHz are ground propagation waves, while the middle frequencies and high frequencies from 300 kHz to 30 MHz are totally sky propagation. The AM radio and citizen band belong to this band. The very high frequency band is mixed between sky and line of sight propagation, ranging from 30 to 300 MHz. FM radio operates in this band. The ultra high frequencies, super high frequencies, and extremely high frequencies all are line of sight propagation, which is ranges from 300 MHz to 300 GHz. Cellular communication system, paging system, satellite communication, ultra high frequency TV, and radar communication are taking place in these bands. Now we are differentiating the wireless transmission by the wave type. There are three types of waves in wireless communication: the radio waves, the microwaves, and infrared waves. Mizan TV offers a course of wireless communication. You can find more about the wireless communication on that course. The link is given in the description. Now the radio waves ranges from 3 kHz to 1 GHz. These waves are omnidirectional. Omnidirectional antennas are used for multicast communication, such as radio and television. Radio waves through sky propagation are a good candidate of long distance broadcasting, such as AM radio. The omnidirectional antenna that transmits signal in all directions. This feature sometimes becomes a disadvantage also, as a far distance antenna may interfere with the frequency of the same frequency antenna. Microwave propagation is line of sight, which require very tall towers far apart from each other. The curvature of the earth as well as other blocking obstacles do not allow to short towers to communicate by using microwaves. Sometimes repeaters are also required for very long distance communication. As we know, the very high frequencies cannot penetrate the walls. This characteristic can be a disadvantage if receivers are inside buildings. The microwave band is relatively wide, almost 299 GHz. Therefore, wider subbands can be assigned and a high data rate is possible. But the use of certain portion of the band requires permission from higher authorities. Microwave needs unidirectional antennas that send out signal in only one direction. The parabolic dish and the horn antenna are mostly used in the microwave communication. The infrared waves ranges between 300 GHz to 400 THz. The wavelength of these waves are from 1 mm to 770 nanometers. Infrared waves are used for short-range communication due to the penetration problem of the signal. This communication is always line of sight and very common in the remote control devices. We can also communicate between devices such as keyboards, mic, PCs, and printers. Device-to-device transfers such as PDA to computer and mobile to mobile through infrared waves. In the next lecture, we will discuss about the subscriber lines. If you like this lecture on Mizan TV, please give a like and comment to the lecture, and also subscribe Mizan TV and press the bell icon for more videos. Thanks a lot.